Let's talk about transforming medicine. What if we could stop using medicine like a blunt instrument? Today, we're diving into a real revolution, targeted nanoscale delivery. It's all about sending these super powerful drugs exactly where they need to go in the body, and absolutely nowhere else. You've probably experienced this, right? Why do so many powerful, even life-saving medications come with this ridiculously long list of side effects? You take something to fix one problem and it feels like it just kicks up 3 more. It's a super common experience, and there's a really basic reason why it happens. So, the heart of the issue is really just a lack of precision. See, most drugs, when they get into your system, they just go everywhere. They kind of flood your whole body to make sure enough of the medicine eventually gets to the right spot. But on that journey, they can mess with perfectly healthy cells. And that is what leads to all those side effects we hate. And this, right here, is what we call medicine's delivery problem. Right now, a lot of medicine works like a scattergun. Just blast it out and hope for the best. But what if we could turn it into a sniper rifle? What if we could design a system that delivers its therapeutic payload directly to one sick cell, while leaving all of its healthy neighbors completely alone? Well, that's the mission. The solution that scientists are working on is happening at a scale that's almost impossible to wrap your head around. We're talking about microscopic vehicles engineered for a critical mission deep inside our bodies. So what exactly is a nanoparticle delivery system? Well, think of it like a tiny, armored package with a high-tech navigation system. It's got 2 main jobs. First, protect the cargo, the drug, from breaking down in the body. And second, act like a GPS-guided missile to deliver that cargo only to the target. And when you do that, you get way better results, and it's much, much safer. And when we say tiny, we really mean it. For most of these medical applications, the delivery vehicles are around 100 nanometers wide. Now, to give you some perspective, a single human hair is about 80,000 nanometers thick. So yeah, we are operating on a truly molecular level here. It's wild. And it's not a one-size-fits-all situation either. Scientists have this whole fleet of nanocarriers they can choose from, each with its own special skills. You've got lipid-based ones. You might know those from mRNA vaccines. They're fantastic for carrying genetic material. Inorganic nanoparticles are the workhorses for treating tumors. Carbon-based ones are incredibly strong. And get this, there are even DNA-based systems built from DNA, which makes them super programmable and body-friendly. Okay, so we have these amazing little vehicles. But how in the world do they know where to go? How do you give a nanoparticle an address? Well, it turns out you give it a kind of built-in GPS using some really clever biochemistry. The secret is all on the surface. Scientists tweak the outside of the nanoparticle by attaching these special molecules called targeting ligands. The absolute best way to picture this is like a key and a lock. The ligand is the key, and it's designed to fit perfectly into one specific lock, a receptor, that you only find on the surface of the cells you're trying to target. And the kinds of keys in this scientific toolkit, they're really diverse and cool. You've got monoclonal antibodies, which are super specific, a favorite for cancer therapies. Peptides are smaller bits of protein. Aptamers are these short, custom-designed strands of DNA or RNA that can be made to bind to pretty much anything. These little ligands are basically the brains of the whole operation. So this all comes together in a pretty neat step-by-step process. First, the nanoparticle gets functionalized. That's when they attach those ligand keys. Then it just cruises through the bloodstream. When it bumps into a target cell, its ligands lock onto the cell's unique receptors. That binding is the signal for the cell to actually pull the entire nanoparticle inside of it. And boom, the package has been delivered. Now, as slick as this system sounds, the journey is not quite that simple. Our bodies are designed to hunt down and get rid of foreign invaders, and these microscopic delivery trucks are no exception. There are some really big hurdles to clear. The number one challenge is our own immune system. It is incredibly good at its job. If it spots these nanoparticles and thinks, hey, you don't belong here, it will attack and clear them out. Now, researchers often try to make them stealthy by coating them in a polymer called PEG, but the body can actually start to make antibodies against the PEG itself. This can cause something called accelerated blood clearance, where on a second dose, the body gets rid of the nanoparticles up to 50 times faster. It basically neutralizes the treatment before it even has a chance to work. And beyond fighting the body's defenses, there's a huge manufacturing problem. And this quote really nails it. Polydispersity just means that in any batch, you've got variation. Imagine trying to bake 1 trillion cookies and getting every single one to come out identical, down to the last atom.
That's the challenge. Unlike a simple drug where every molecule is the same, making every single nanoparticle uniform is just incredibly tough, and that lack of consistency can really mess with both safety and how well it works.
Okay, so let's imagine our little nanoparticle has dodged the immune system, it's found its target cell, and it's been pulled inside. Mission accomplished, right? Well, not quite. There is one final barrier it has to get past. So when the cell brings the nanoparticle inside, it traps it in this little bubble called an endosome. Now, if the nanoparticle just stays stuck in there, its drug cargo can't get out to do its job, and the cell will eventually just destroy it. So the nanoparticle has to pull off one last prison break. It's called endosomal escape. It has to break out of that bubble and release its therapeutic payload into the cell's main area, the cytoplasm. Only then, finally, can the medicine actually start to work. So yeah, the challenges are pretty significant, but the potential payoff for clearing these hurdles, it's nothing short of world-changing. Let's take a look at what the future of nanomedicine could really be. We're already seeing the first wave of these treatments. For cancer, nanomedicines like GenXL PM are delivering chemo right to tumors, which means higher doses with fewer side effects. In gene therapy, they're being designed to carry CRISPR gene editing tools right to the source of a genetic defect. We've all seen the power of lipid nanoparticles in vaccines, and we know the platform is durable. And for inherited disorders, it's a way to deliver missing enzymes that the body just can't make itself. What all of this is really pointing to is a massive shift in how we even think about medicine. We are moving way beyond just discovering new drugs. We are now learning how to engineer delivery systems at the most fundamental level, basically treating biology itself as a system that we can program with incredible precision. So here's the big takeaway. We are right at the beginning of a whole new era. Being able to target specific cells just blows the doors open to possibilities we're only starting to imagine. And it makes you ask a really powerful question. As we get better and better at this, as we truly master the art of delivering medicine to one single cell at a time, what challenges that seem completely impossible today will become solvable tomorrow?